Hi, my name is Arturo Pascuzzo and I'm going to present this research which focuses on analysis for the identification of proper strategies to improve the structural integrity of tight arc ridges affected by instability phenomena. Tight arc ridges have been traditionally employed to overcome short span lengths. However, during the last decades, the structures have become very competitive to cable-stayed bridges in the field of medium span lengths, and probably they will be an effective solution to overcome long spans in the next future. Tight arc bridges ensure relevant advantages from both structural and economic points of view. In addition, the structures are aesthetically attractive. Recently, several examples of finite structures have been realized, such as the Infinity Bridge, a pedestrian bridge that was realized in 2008 in England. The structure of a tight arc bridge is composed of two arc ribs which sustain a lower deck by means of several anchor cables. In particular, the deck ties the arc ribs to extremities together, thus supporting the arc horizontal thrust. The anchor arrangement classifies tight arc bridges. In particular, two main configurations are usually adopted. The first is the moment-tied configuration, and the second is the network configuration. The moment-tied configuration consists of several vertical anchors equally spaced along the tie girders. The network configuration is composed of the union of two specular planes of inclined anchors forming a net layout. The arc ribs may be arranged vertically or inclined inwardly, and are usually braced by means of a wind bracing system to ensure a proper capacity against out-of-plane buckling phenomena. The most frequent configuration for the wind bracing system are the Virendel, X-shaped or K-shaped configuration. This structure presents several key features and structural problems. Firstly, the identification of the initial configuration, which consists in the definition of initial stress in cable elements to achieve an undeformed configuration of the structure under dead loads. Secondly, the structure is highly susceptible to buckling phenomena, because the arc ribs are mainly subjected to compression forces. Buckling phenomena are highly dangerous, since may compromise the integrity of the wall structure. In this context, the nonlinear behavior of tight arc bridges with inclined arc have been scarcely investigated, thus representing one of the main issues that should be properly addressed. On the basis of the previous consideration, with this work we developed an investigation of nonlinear behavior of tight arc bridges with arc ribs inclined inwardly. In addition, we assessed the benefits induced by arc rib inclination on the buckling capacity of the structure from both economic and structural points of view. The presentation is organized as follows. Firstly, we propose a brief review of the existing recommendation provided by Eurocode 3 regarding the buckling design of tight arc bridges, and a review of the most common buckling analysis methods. Secondly, we present the numerical model employed for the study. Finally, we show results and the main conclusion of the work. Prescription for the out-of-plane buckling design of tight arc bridges are reported in Part 2 of Eurocode 3, which treats the design of steel bridges. Eurocode 3 proposes a simplified method for the buckling design of tight arc bridges, which analyzes the buckling capacity of the end portals of the structure, which consist of the unbraced portions of the arc ribs. In particular, the method quantifies the critical cast forces of the ribs by using buckling factors defined for truss structures. This method is easy to use, but presents several limitations. In particular, the wind bracing typology is not considered. The method refers exclusively to moment-tied arc bridges. Inclined arc ribs configuration are not considered. Alternatively to the simplified method proposed by Eurocode 3, the nonlinear behavior of a tight arc bridge may be investigated by using numerical analysis. In particular, two different analyses can be adopted. The first is the traditional elastic buckling analysis, and the second is the nonlinear elastic analysis. The elastic buckling analysis is based on an eigenvalue solution obtained starting from the linearized deformed configuration of the structure. This method evaluates the eigenvalues, which represent the critical load multiplier of the structure, and the corresponding eigenmode or critical buckling shapes. The elastic buckling analysis requires low computational effort, However, it involves a considerable simplification of nonlinear behavior of the structure, thus leading to overestimation of a buckling capacity. On the other hand, nonlinear elastic analysis provides more accurate results, since it considers the path-dependent nature of the applied loads, taking into account the actual deformation involved in the structural system. The nonlinear elastic analysis ensures an accurate evaluation of the critical buckling capacity of the structure. However, it may be computationally expensive, thus being prohibited for more complex structures. Moreover, a proper initial out-of-plane configuration should be imposed to the structure to ensure out-of-plane displacement. Note that this initial configuration can affect the prediction of the buckling capacity, thus representing the most relevant aspect of the method. In this work, we present a new method for the analysis of tire bridges. The nonlinear behavior is investigated by means of an advanced numerical model in which the arc creep, the tie girder, and the arc transversal beams are modeled by using Timoshenko nonlinear beam elements, whereas truss elements are adopted for the hangers. In particular, the hangers are divided into a number of elements according to the multi-element cable system approach, which permits to reproduce any source of linearities of cables. Both arc and girder are connected to the cable system by means of explicit constraint equation, defined at intersection nodes of beam and truss elements. A fundamental task to be achieved is the definition of an initial geometric and stress configuration of the reaction of permanent and dead loads. This is quite important for the purpose of the investigation, since nonlinear behavior is strongly dependent from the initial stress distribution. From the design point of view, it is required to calculate initial stress in the hangers and the position of the arc and girder able to enforce the bridge in a deformed design configuration under the action of dead and permanent loads. This goal has been obtained by using a numerical procedure based on the zero displacement method, which consists to solve a constraint optimization problem defined throughout displacement and stress constraint condition. In particular, the unknown quantities are represented by initial stress of the hanger, global axial average deformation of the girder and the arc. The unknowns of the problems are expressed as a combination of a constant quantity that have to be corrected by an incremental contribution. By this way, the problem can be solved with low computational efforts. The constraint conditions are expressed as a function of the vertical displacement of the hanger at the girder-hanger connection, the horizontal displacement of the girder, and vertical displacement at the top arc cross-section. The numerical model was investigated by using an analysis method which combines results relative to traditional elastic buckling analysis and nonlinear elastic analysis. The method is articulated in three main steps. The first step consists in the definition of the bridge geometry. Subsequently, an elastic buckling analysis is performed. In this framework, hangers should be meshed with one single element, since the analysis do not account for nonlinearities of cables. The buckling analysis provides the critical buckling loads and the corresponding mode shapes. Finally, a nonlinear analysis of the structure is performed. In this case, hangers are discretized in several truss elements, according to multi-truss element approach. A fundamental task in the nonlinear analysis is the definition of a proper out-of-plane configuration of the structure to capture the buckling mechanism. The initial out-of-plane configuration is imposed to the structure, reproducing the first critical buckling shapes of the structure, which allow out-of-plane amplitude. Starting from this configuration, live loads are progressively increased up to the creases of the structure. The investigation is performed assuming a steel tie arc bridge of 150 meters with a bridge deck of 15 meters. The rise of the arcs is equal to 27 meters. Arc ribs and tie girder are made of steel and have rectangular hollow cross-sections, whereas pipe elements are assumed for the beams of the wind bracing system. The cable system consists of 18 hangers equally spaced along the girder every 7.5 meters. The hanger can be arranged in vertical or network configurations. In the last case, the angle are split in two specular subsystems of 9 elements inclined with a variable angle with respect to the horizontal. Dead loads concerning structural and non-structural loads are equal to 200 kN per meters, whereas live loads are assumed about 116 kN per meters, which consists of two lines of the LM71 train model, described in Eurocode 1, that acts on the whole bridge length. At first, we developed a comparison between results relative to bridge configuration with vertical and inward inclined arc ribs. The analysis was performed using two structures with momental configuration for the cable system and the Rendell scheme for the wind bracing system. From the results, it transpired that traditional elastic buckling analysis overestimates the maximum capacity of the bridges, thus denoting how nonlinearities of the structures largely affect the out-of-plane buckling behavior. In addition, the results highlight that arc rib inclination highly improves the integrity of the structures against out-of-plane buckling mechanisms, since the live load multiplier predicted by nonlinear elastic analysis increased significantly. Such behavior can be explained by analyzing the buckling modes and the deformance shapes at failure. In the case of inclined arcs, the center of the structure behaves rigidly, whereas the side zone are affected by relevant lateral displacement as well as larger bending deformations. These mechanisms similarly occur in traditional tire bridge structures with vertical ribs based on being on K-shaped wind bracing system, where side zone works as portal structures. A number of studies reported in the literature have remarked that this behavior provides excellent performance against out-of-plane buckling mechanisms. Other results were developed with the aim to analyze the variability of the critical axial force in arc ribs in terms of the arc slope. The analysis was performed comparing two bracing system configurations, the Rendell and the K-shaped configuration. Here, the critical axial force has been normalized with respect to the yield axial force, which has been defined considering a steel of 350 MPa. The results show that the arc rib inclination largely improved the integrity of the structure based by means of a Rendell bracing system, since the critical axial force increased for increments of the rib inclination. In particular, the out-of-plane back increases of the structure is completely avoided when the rib slope is larger than 8 degrees. On the other hand, the K-shaped bracing system ensures measuring of safety against out-of-plane buckling phenomena for any value of the arc rib inclination. In particular, the critical axial force keeps a small constant and equal to 2.1. A possible explanation for this might be that K-shaped bracing system stiff the ribs so hard to make irrelevant the stiffness provided by the arc rib inclination. However, the structural integrity of tire bridges with vertical ribs braced by means of a K-shaped bracing system highly depends on the lateral stiffness of the bridge and portals. This stiffness is highly influenced by the type of mutual connection between the arc ribs and tire girder extremities. These results show that the capacity of the structure with vertical arcs braced by means of a K-shaped bracing system suddenly decrease when the hinges are adopted. By inclining the arc ribs, this behavior is avoided, since the nonlinear behavior of the structure is unaffected by the kind of joints between rib and tire extremities. This behavior may be explained by the fact that rib inclination leads to a bridge structure characterized by an A-shaped transversal geometrical configuration, which provides a notable lateral stiffness mainly due to its geometry. This aspect provides great advantages in the case of long span lengths, since less economic resources may be employed to brace the structure. Here we compare inclined and vertical tire bridge configuration for increasing span lengths, from structural and economic points of view. In particular, with regard to the economic aspect, the study focused attention on the overall amount of steel involved in the bracing system, which represents one of the most expensive parts of the entire structure due to the high cost of manufacturing process per unit of volume. The results show that arc rib inclination can be efficiently employed in the file of large spans, since the bridge presents excellent structural behavior. In addition, arc inclination ensures significant economic benefits, since the overall amount of material needed for the bracing system is lower than the required for the traditional scheme based on vertical arcs. In conclusion, this work examined the effectiveness of arc-rib inclination as a strategy designed to increase the structural integrity of tire bridges against out-of-plane buckling phenomena. The results have revealed that the nonlinear analysis should be used to properly quantify the buckling capacity of tire bridges. As a matter of fact, traditional elastic buckling analysis may involve relevant overestimations. Arc-rib inclination improves the nonlinear behavior of the structure. The inclination creates a high stiff region along the center of the structure, which contributes to reduce the effective buckling length of the ribs. In addition, the structure assumes transversally an U-shaped configuration, which contributes to enhance the overall lateral stiffness of the bridge structure, mainly by means of geometry. Finally, inclination contributes to reduce the construction cost, since the amount of materials and manufacturing processes required for the element of the braking system are reduced. Thank you for watching.